Yes, good morning, good evening, wherever you are as part of this wonderful global community. Really good talks so far. Yeah, my name is Dustin Hammerla. I'm a manager of ML engineering here at Disney Streaming, and we are building, or my team is building, our internal feature store that is powering various ML use cases across all of the Disney streaming apps. And for those that don't know, that's not just Disney Plus, but also Hulu, Star Plus, and ESPN Plus. The agenda for my talk is pretty straightforward. I want to kind of start off with an overview and the motivation to what led us building our own feature store, and then talk more about its capabilities and what problems we're solving with our feature store, and then kind of pull back the curtain on implementation and architecture. So yeah, taking a quick step back, I know this is obviously a feature store summit, but our feature store is part of a larger ML platform that we call Nexus. And you know, Nexus obviously aims to democratize and accelerate ML development across all of Disney streaming. And there's 4 other main components as part of this ML platform. So we have the model engineering system that consists of our real-time inference infrastructure. So data scientists, machine learning engineers interact with this component to kind of develop and deploy their models. And we have a workflow management system, just kind of an Airflow on steroids, where practitioners can schedule and execute various workflows, so batch training and batch inference, for example. And then we have a context and event processor. So since we are a general purpose, there's a lot of config files and context going on across different use cases. So we want to provide the ability to define this context and these configurations in a central system and not kind of buried inside ML code. And then when we were talking about nearline inference, we give our practitioners the ability to kind of specify what types of events the pipeline has to listen to that would then trigger inference. And then lastly, we have an online metrics component that allows us to track performance of our models in real time. So with this in mind, obviously compatibility and being able to customize the APIs so that our feature store would interact nicely with the other components was definitely a driving factor for when we decided on architecture and build versus buy. But again, why did we start on this journey? And probably some repetition here, but we needed a way to improve how features are created and how they are consumed, because what we saw in our legacy pipelines were kind of these bespoke pipelines where data scientists would kind of define and run their feature transformation code alongside model training and inference. And so you would not only repeat the development work there, but also kind of repeat the compute. And so with the feature store kind of in the middle, we're decoupling these 2 steps and have different computing environments ingesting features. So this can be batch processing or stream processing, and then different computing environments reading features back, be it in batch for training or inference, or using our real-time inference infrastructure to kind of fetch features in a low latency fashion. And so unifying all of these ways how features can be generate and how they can be consumed. It's I think one of our main value adds, or one of our key factors that I also want to talk about more on the upcoming slides. And then, of course, if you register features in the feature store, then they become discoverable and shareable, and you know, we really reduce the time to the next model. And so again, you know, one could say I've seen this before. This was kind of the general motivation when we started to look into the concept of feature stores. We looked into the market, and then we realized, okay, seems like we have some additional requirements. And at the time, which again is over a year ago, we saw that you know, existing products weren't really meeting some of these. And you know, most of it has to do with our global scale batch training and scoring. So Z+ is obviously available around the world, and we train regionally specific models that then need to be fed regionally specific data. And then if you add experimentation to this, where we potentially feed different slices of the training or inference data based on user segmentation, and we're running a A/B test, for example, that kind of data distribution, we wanted that to be kind of native to the feature store. And then another thing that we saw in kind of the third-party offerings was the concept of one training data set, which, at least for part of our use cases, wasn't really the case. We needed to, I mean, surely we had one training or inference data set, but we would additionally have to be able to manage other data sets as well. So potentially some contextual data sets. Think of pairs of recommendations that you don't want to necessarily appear together, especially kind of in a family-friendly environment like Disney+. So being able to kind of specify multiple data sets, doing this natively through the feature store was another requirement. And then, you know, the way we were running our data prep jobs was, or is in Spark, but our training and scoring runs in kind of a Dockerized single node environment on AWS Batch, where we have, you know, multiple instances of a model, but we don't have Spark to distribute that data to these specific single nodes. And here we kind of had to get creative. I'm going to talk more about this one, where we kind of build our own distribution engine to bridge this gap. And then I've spoken about the compatibility with the larger platform. That was a driving factor. And kind of organizationally, we had legacy infrastructure and teams in place that were ready and eager to kind of get going with the kind of next evolution of our ML infrastructure and building out feature store. Yeah, so that's kind of how we started on our own journey to building our internal feature store. Okay, yeah, what pain points do we solve with Nexus, and you know, what are the feature store capabilities? And you know, looking at some of the other talks, it's never a single sentence of what the value add is of a feature store and what problems it solves. It's at least always a paragraph or more. And so when I explain to someone what do we solve with feature store, we kind of use this framework of a capability map, where we define or distinguish between auxiliary capabilities. So here we have a feature store UI where engineers can go and kind of discover new feature data sets and features. We have statistics and validations that can run once data arrives at the feature store to kind of provide intelligence and data quality assurance. We have SDKs in Python and Scala. We have feature transformations. So for us, at least at this point, it is more of an auxiliary capability. I know some other teams have focused more on the transform part, but yeah, for us, it's a shared library. It's kind of a CI/CD tool stack to be able to deploy feature transformations really easily. Point-in-time joins, a sandbox environment that allows practitioners to kind of iterate and experiment with new feature data sets outside of the production environment. Yeah, but these are kind of on top of what we call our core capabilities, which is really around data transportation in a way. So these, we kind of see data transport is kind of at the center of, how do you compute and write features and how do you read them? And because there's so many options available for different use cases, and I'm kind of gonna walk through these different modes. So when you're writing your feature transformations in batch and you're reading in batch and you're doing this in Spark, there's no big magic here. We're using Spark data frames. But then I've alluded at this before, but if you then want to consume this large data and potentially a subset, maybe a subpartition for a regional data set, or you're specifying some memory constraint where you only want to read a subsample of the data set based on like a max memory requirement, then you really can't use Spark to kind of identify your files. And so here we built a service endpoint where a one-node consumer can query our API and kind of get file pointers back, so it can then read that subset of the data into its one-node environment. And then moving over, if we want to read features in real time, we then have another feature store mechanism where we sync the data. So we process it and generate it in batch, but then we sync it to our online key value store. And then moving down to another kind of mode of computation, which is stream processing. Here we offer the ability to generate the features in stream and then ingest them into the offline store, as well as ingest them directly to the online store. And then a third category that we see is kind of real-time compute, where we can say feature transformations with the feature store, kind of model-specific feature transformations. And you can apply those UDFs on the batch data, as well as compute in real time on, for example, an inference context. And then lastly, another mechanism is the feature logging. So no matter how you decide to generate your features, at inference, we can save the entire feature vector, the final feature vector, into our offline store to make it available for batch reads. Yeah, and so we use this kind of framework to organize our own work and roadmap, and it's been definitely really helpful. And then also when we have to support so many different use cases, and any particular use case can kind of pick and choose their mechanisms and kind of their pathway to their data. Yeah, let me take a little bit of time. Okay, so looking a little bit closer at implementation architecture. So essentially our feature store consists of 4 main components. We use Delta Lake on S3 for our offline store. We have a feature registry, or the brain of the whole system, which is a service on top of a Postgres DB to store all metadata related to features. And then we have a separate low latency online feature service on top of Redis cluster Elastic Cache to serve all of the low latency, high throughput reads and writes. And then we have client SDKs in Scala and Python. And to, I mentioned there's many different options how data can flow through this system for different use cases, but kind of picking one of them and showing some kind of pseudo code to make things more tangible. Let's look at how our system operates when we're writing data in Spark and we're reading it in kind of a non-Spark environment. So we distinguish between two different classes. So we have feature groups that are kind of potentially model agnostic, general data sets across models that data engineers prepare. And then we have a feature service object that a data scientist or machine learning engineer would prepare for a specific model. So there we can say there's a one-to-one relationship between a feature service and a specific model, where we can then tie together different feature groups, for example, for one specific model, specifying joins and things like that. And so, when we're running this pipeline, we would, the Spark job, for example, would use the SDK to pull its metadata, connect to the feature store, get a feature store object, get one or many feature groups. So in this example, we already assume that the feature groups have already been populated by a previous step. We then create a feature service and then ingest that kind of training data to the feature service and register it with our distribution engine. And then at read time, model wakes up, again, uses SDK to get its feature service, and then it could use the feature service to query a subsample of the data. So we're running, multiple instances of a regional model. We would query just that regional specific data and kind of distribute it using natively our feature store. Okay, yeah, and then moving over to kind of the stream write real-time read scenario. The streaming job would again get metadata from the registry, and also here we use the same concept of feature groups to organize the online data as well. So we serialize the protobuf and kind of build key building logic to kind of build the hash keys and write this data to the online feature service. And then for reading features back for real-time inference, we provide a join API that gives us a query plan that kind of specifies which feature groups have to be fetched, and kind of also we can translate this query plan from a kind of generic representation to kind of a Redis type query read plan. So we would save the query plan with the feature service, and then when the model is deployed into the real-time inference infrastructure, it would wake up, again, load its feature service, and then could run this kind of get feature vector method to retrieve a feature vector in milliseconds by passing primary keys from a real-time request. And I think I'm good on time. That's it. Thanks for your attention, but also thank you to the Feature Store and data engineering community, especially the open source projects like Feast and Hopsworks that were definitely a great inspiration for some of the things that we had to solve as well. So thanks for having me.